In this video, we're going to look at the bonding of transition metals and rationalize some of their color and magnetic properties in that regard. You'll find it helpful if you have a periodic table at hand, and I will quickly sketch out the first row that covers the transition metals, but the full periodic table will be handy during the later part of this video. So we have potassium and calcium as the first two members of the series, and then scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. The first two elements are the 4s2 electrons. These are the ones that are really quite easily ionized, and these are the true transition elements, that have the 3d electrons. So for instance, if we wanted to look at the titanium 3+ ion, then being in the fourth column from the left hand side, losing 3 electrons would mean that we would have 1 left, and that would be described as a D1. The titanium 4+, on the other hand, would lose all its electrons and would become a D0. Similarly, the vanadium 4+ would lose all 4 electrons and have the 5th one remaining to make it a D1. And the vanadium 5+ would lose the lot and it would become D0. So you can see where we're going with this. We're going to be looking at how a metal of N+ charge behaves in terms of bonding. In the bonding theory that you will have encountered up until now, you will have come across valence bond theory, which gave us the idea of hybridization to create equal energy orbitals, and these could also incorporate D orbitals. The trouble with this theory, its limitations, is that we ran out of D orbitals that were easily accessible for the transition elements on the right hand side of the table. The D orbitals that were needed were in the next shell up and considered to be of rather too high energy to be accessed. And so this is where valence bond theory kind of creeps to a halt. What we can take away from it is that we have 5 equal energy orbitals, 5 D orbitals. And we will now start looking at how equal they are. Well, if we consider that our metal N+ is in the presence of ligands, but they're a long way away, then our 5 D orbitals remain unfazed. But if we bring those ligands close to, they create electrostatic charge. If we consider that it's a spherically symmetrical charge coming in from these ligands, then all 5 D orbitals will be raised in energy as a result of that electron-electron repulsion. So this is where we have electrostatic repulsion. And we've now raised the energy of the orbitals of an indeterminate amount, but ligands here were distant, and now they're getting closer. And of course we use the term L for ligands. Okay. Crystal field theory now talks about how that electrostatic field theory will affect the different orbitals. Because rather than creating a spherically symmetrical cloud, they're going to be considered as the ligands are point sources of charge. So let's backtrack a little bit, and you recall that the shapes of the d orbitals are typically, let's draw some axes in first of all. So most of the d orbitals usually have this kind of shape. Double lobes, and then there's two pairs if you compare them to the p orbital. Okay, and it turns out that if this was the xy axis, then what I've drawn would be the dxy orbital. And by relabeling the axes x and z or y and z, we can similarly draw these three orbitals. They all look exactly the same. Now, if we draw the dx squared minus y squared orbitals, they look something like this. Whereas the dz squared orbital has this rather peculiar shape. In fact, the dz squared is a linear combination of two different orbitals. It's the dz squared minus x squared and the dz squared minus y squared. But mathematically, it's combined into the dz squared to just give us the 5 orbitals that the Schrödinger equation indicates. The important thing here is that these orbitals to the left of this vertical line are all in between axes. Whereas these orbitals are aligned with the axes. And if we consider our octahedral metal with 6 ligands, which crystal field theory says that we must treat them as point sources of charge, there will be a greater electrostatic repulsion when the ligand electron is interacting with the metal electron that is in the dx squared or the dz squared than if it was interacting with the dxy or dyz and so on electron, because that latter orbital is in between the axes. And so you can see that we've now taken our 5 equal energy orbitals and made 2 of them slightly less favorable because they're now of higher energy as a result of that electrostatic interaction and repulsion. And we've made 3 of them of slightly favorable energy relative to our previous diagram. If we consider that we have a center of gravity, if you like, there we can show that this gap should be 2/5 relative to this gap of 3/5. And you can see that the 2 and 3 come from the opposite number of orbitals to keep the whole thing energetically neutral relative to the previous diagram. And the size of the unit here is usually given the term delta. And delta in the octahedral case often has a subscript O or oct. And in old terminology, it would have been written as 10 dq, which had some mathematical reasons for being labeled as such, but modern literature almost always uses delta octahedral now. The crystal field theory has also been shown to have its limitations, and molecular orbital theory uses the same concept but relabels the orbitals, and we can treat these just as labels at this stage, but the lower set are triply degenerate because there's 3 of them, and so they have the label T2, and the doubly degenerate has the label E. The G signifies that it's an octahedral arrangement, very symmetrical. Gerade is the German term, and that's where the G comes from. But all of this is derived from group theory, which is a bit beyond where we're going here. So you can just treat them as labels. So T2G for the lower ones and EG for the upper ones in an octahedral environment. Okay, so we now have this kind of arrangement for our orbitals. The dxy, dyz, and dxz, and the dx squared minus y squared, or dz squared, and these would be EG and T2G. So for our example of titanium 3+, it was a D1 case. And so when we put in our electron into the arrangement, obviously it's going to go into the lowest energy that's more favorable, and that's a ground state. If we put in our second electron, so let's consider the problem is now vanadium 3+, it's a D2, and there's a rule that says that the electron cannot go into the orbital, the first orbital, it has to go into the second orbital, and Hund's rule says that it has to go in with the same spin, a parallel spin, and so we're required to put it in as indicated there. If we now extend this to the chromium 3+ example, then we have 3 d electrons to worry about, and of course the third electron must go in there. If we look at the relatively rare manganese 3+ ion, which would be a D4, or perhaps this might even be an iron 4+, for instance, where do we put the fourth electron? That's the interesting question here. We've got 2 possibilities. One would be to put it into one of these orbitals and pair it up, and the other would be to put it in the higher energy. So if we were to put it in the higher energy, it was going to go up there, or the alternative was to pair it up like this. This arrangement is termed high spin, and this is low spin. And you can see by continuing with this series that as you have more d electrons in your problem, you can now build up patterns that have alternatives of high spin or low spin. Now this has some interesting consequences because, well, first of all, let's talk about the color. The gap between these orbitals we talked about as being delta. So if we have an electron down here, and it doesn't matter whether it's one of many or just one on its own, in the ground state it is in the T2G orbitals, but if we excite it, then it can go up here to the excited state. It's acquired some energy, and it so happens that energy is in the same range as light that we can see, visible light. So you can imagine that a transition metal complex in daylight is going to absorb some visible light and be excited, And what we see with our eyes is the rest of the light that's reflected back. So some of the light is absorbed and the rest reflects back to us. Since that's in the visible range, we see it as colored. And so many, but not all, transition metal complexes are colored. And it's where you can excite an electron up and get absorption of visible light. The other consequence is in magnetism. You can see from the example above that in the D4 case, if it's high spin, then we can have 4 unpaired electrons. Or we could have the low spin case with 2 unpaired electrons. Now it so happens that unpaired electrons behave differently in a magnetic field to paired electrons. Unpaired electrons are paramagnetic and they're drawn into a magnetic field, whereas paired electrons are diamagnetic and they're weakly repelled from a magnetic field. So if we were to do some measurements, some magnetic measurements on our complexes, we should be able to get a measure of how many unpaired electrons we have. There are several ways of doing the actual experiment, and I don't really want to go into that at this stage, but usually you can get a rough estimate of the number of unpaired electrons, bearing in mind that we only want to deal in whole numbers of unpaired electrons. It can get more sophisticated looking at deviations from the theory, but in general, that's where we're going to go with just looking for whole numbers of electrons at this stage. So we are now in a position, by being able to measure magnetic susceptibility and therefore determine the number of unpaired electrons per molecule, to actually start rationalizing the theory and determining whether a compound has its metal in its high spin state or low spin state with the number of unpaired electrons that have been indicated from the experiment. What I'd like you to do is to continue adding the number of electrons to the pattern and see whether high spin and low spin can be defined in all cases or only some cases by doing these magnetic experiments. Now, looking at the tetrahedral case is slightly different. If you put a metal into a cubic environment, and we'll have the center of the metal there, and you can then draw the tetrahedron by choosing atoms at alternate corners and then joining them up with their center. And this gives us the tetrahedral arrangement, which is more commonly drawn, something along those lines there. And it so happens that the electrostatic interactions in the ML4 case cause the arrangement of the d orbitals to flip upside down for the same reasons as we discussed with the octahedral. Slightly more difficult to explain mathematically, but it can be done. And so we end up with 3 higher energy orbitals and 2 lower ones. Still called E and still called T2, but no G. The G indicated a high degree of symmetry in the octahedral arrangement, and in the tetrahedral arrangement that symmetry is not quite there, so the G is left off, again for reasons found in group theory. So when we start to put in our electrons, the same issue applies. We can put the first one in here for D1, for D2 has to go in here. And now for the D3, we have the option of the low spin case or the high spin case. It so happens that the high spin case is almost always the situation. And the reason is because the gap here, delta, is always compared to another energy, P, which is the pairing energy. And in some cases, particularly in the octahedral arrangement, there's a balance between delta and P. It takes some energy to pair an electron up, and that energy is measured by P. It takes some energy to put it into the higher orbital, and that is measured by delta. So if delta is much greater than the pairing energy, then we get the low spin case. If delta is less than the pairing energy, then we get the high spin case. Now, in the tetrahedral examples, it so happens that delta T is almost always lower than the pairing energy. And consequently, we always or invariably have the high spin examples for tetrahedral. Whereas in the octahedral arrangement, it is high spin and low spin can vary. The variation of delta is an interesting measurement in itself, whether it's delta octahedral or delta tetrahedral, because you can look at different series, and so you can look at a series with the same Mn plus and vary L, and you will end up with a spectrochemical series which is a measurement of the size of delta for each ligand, and it follows a fairly logical sequence. You can also do it the other way around. So look at delta, and to look at it, as you recall, it could be a measurement of the absorption spectrum. You can keep the same L and vary either M or M plus, and you end up with a far more erratic series that is a little more difficult to correlate. But the first series that I mentioned is quite a common one that's mentioned a lot, and there is a fair bit of logic attached to how it's put together. So now what I think would be most illustrative is if you construct a table. And this will be a case of D1, D2, D3, and look at the octahedral of high spin, low spin, and the tetrahedral high spin, and the theoretical low spin as well, and make up the whole table. It's not a table that needs to be memorized. It's the construction of the table that is the learning exercise, and you can see where distinctions could be found experimentally or perhaps not.